Okay, now I would also like to, just as we are getting familiar with the whole process of sampling, the spectral representation, I would like to spend a little bit of time on the spectral part. But before we go there, let me ask you a question that I hope will be an interesting one for you to explore. So, you have understood how the continuous time music signal is recorded onto a CD format. Okay. You apply an anti-aliasing filter, you sample it, in fact oversample it, apply a digital filter and then downsample. Okay. So, you have got the overall feel for it. Okay. Now, this is a applied question. Compact disc was trying to sample at 44.1 kilohertz when the range of interest was 0 to 20 kilohertz. Now, digital audio tape, we mentioned it is a format that is not very commonly used, but it has been used quite extensively in the past, 48 kilohertz. Just on the basis of what you have studied or what we have seen so far, does the DAT have any advantage over the CD? Just on the basis of both are eventually going to produce 16-bit or 22-bit representation of the signals. Is there any advantage that DAT would have over the CD, or if you were the designer, would you have any reason to increase the sampling rate? Anti-aliasing filter? Okay, that, or you may think, why do I bother with oversampling? Maybe I can do with normal sampling. I will just sample it at 48 kilohertz. My analog filter is now has got a little bit more room to be designed. It's not as sharp as what you would have for a CD player. So I may not need to go to. Again, now what would be the trade-off? Why you would want to do that when going to oversampling and coming down would be, but it's an interesting question. But it does have the following advantages that you could work without oversampling. Okay, that is one possibility. The second one, of course, was, as rightly pointed out, would be lower complexity for your digital filter. Lower complexity for the digital anti-aliasing filter. Anti-aliasing filter. Okay, and basically what this one is implying is that there is a lower complexity for the anti-aliasing analog filter without oversampling, okay, compared to the CD case without oversampling. That's what. Okay, so ultimately it is our ability to understand the constraints and be very clear about what are the concepts, what helps me, what hurts me, and then take advantage of that. Okay, very quickly let's move into some of the things that we wanted to cover in today's class. Okay, back to the example, let me call it as example 1B. It is the same example as before, but as I mentioned, we are trying to bring out newer elements. So, xc of t is cosine 4000 pi t, 4000 pi t. So, I am interested in getting xc of j omega. So, we write this as 1/2 of e power j 4000 pi t plus e power minus j 4000 pi t. Okay. So, this one basically using the Fourier transform of a complex exponential, this would be pi times delta, Dirac delta of omega minus 4000 pi plus delta of omega plus 4000 pi. Okay, again these are all probably very basic things for you, but it's important for us so that we can derive the key results that we are looking for. So in the spectral domain, so I will have two Dirac deltas for the continuous time frequency. So if this is 0, 1 Dirac delta at 4000 pi radians per second, the other one at minus 4000 pi radians per second. Do not forget to mention the height of the impulses, that scale factor is pi, that will be important for us so that we do not lose out on the scaling aspects. Okay, so the height is pi. Okay, now I have sampled it at Ts is equal to 1 over 6000, which means my sampling frequency is 12,000 pi, and the sampled spectrum xs of j omega is pi over Ts. Please remember, don't miss out the pi. This is part of the spectrum of the input signal. So pi over Ts summation k equal to minus infinity to infinity delta of omega minus 4000 pi plus replicas which are spaced at omega s. You can do plus or minus k, it does not matter, minus k omega s plus delta of omega plus 4000 pi minus k omega s. Basically the original spectrum shifted. So what I would like to do is sketch this spectrum again just for the purposes of illustrating the key concepts. So the first copy of the signal corresponding to k equal to 0, I have at 4000 pi and at minus 4000 pi. This corresponds to, green corresponds to k equal to 0. Then k equal to 1 will be centered around 12,000 pi, right, that is the first shift, and it will produce two copies of the signal, one sitting at 8000 pi. Let me just mark these. The blue green ones are 4000 pi minus 4000 pi. Red one is 8000 pi. It is plus minus 4000 pi from 12,000 pi. So the other one will be sitting at 16,000 pi. Okay, I am sure this is fairly easy to follow. K equal to 1, and just for completeness, let us do k equal to minus 1, and that will be at minus 12,000 pi and producing impulses at minus 8,000 and minus 12,000. So this is k equal to minus 1, and likewise you would basically fill up the entire space. So this is minus 8,000 pi minus 16,000 pi. Okay. Now two reasons for drawing this. One is to first of all visualize the replication of spectrum, but more importantly the process of reconstruction. So if I want to go from the sampled signal back to the continuous time signal, then I must remove these unwanted images. And we said in the last class that the reconstruction process basically will retain everything from minus omega s by 2 to omega s by 2, minus omega s by 2 to omega s by 2. Okay. What is omega s for us here? Omega s is equal to 12,000 pi. 12,000 pi. So, omega s by 2 to omega s minus omega s by 2. So, let us just mark that portion, that will be from minus 6,000 to plus 6,000. That is the reconstruction process. So, that is minus 6,000 pi to 6,000 pi. Everything that is preserved inside is what will be retained, all other images removed, which basically says that when you do the reconstruction process using our standard definition of what is going to be retained by the reconstruction filter, what is going to be removed, what you get at the after reconstruction is exactly what went into your sampling process. Okay. Now, do not forget the scale factor. This one had a scale factor of pi over Ts. So, each of these will be pi over Ts. Your reconstruction filter will have an amplitude Ts, if you recall we specified that. So, when I multiply the two, this will come out to be pi. That's the input spectrum. Okay, which is what we started off with. Okay, so so far everything is clean, everything is clear. Now, here is where it becomes an important example, and that is the whole reason of doing this, is so that we can actually take it to the last step. So, this is example 1C, or the third time we are looking at the same example. So, xc of t is cosine 4000 pi t, nothing has changed. The sampling period is Ts prime, which is now 1 by 1500. So, basically I have gone to a lower sampling frequency, basically it has gone down to 1500 hertz from 6000 hertz. Okay. First question is what is my discrete time signal? So, x of n will be cosine 4000 pi times n times Ts. Ts is 1 by 1500, cosine 4000 pi n by 1500. Please simplify this, you will find that what you get is cosine 2 pi by 3n. The same discrete time signal, that is, in other words, the same expression for the discrete time signal. You are not surprised, because you expect that when you undersample, you will get an alias signal. It so turns out that this alias signal is exactly the same signal that came before. Okay, that's effect of aliasing. We are not surprised now, but please look at it on the spectral side. Okay, that is what is important for us. So, as before, the original copy of the spectrum is at 4000 pi and minus 4000 pi. Just to simplify, with your permission, I am going to do the scale multiplied, basically whatever we write on the scale as multiplied by 1000 pi. Okay, so you do not have to keep writing these big numbers. Okay, whatever is written on the scale is multiplied. So, the impulses are at plus 4 and at minus 4. Let me just label it correctly so that it will be easy for us to. Okay, so if this is 0, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8. Okay, if this is 0, 1, 2, 3, 4, that is where one of the first the input spectrum, minus 1, 2, 3, 4, that is where this spectrum is going to be. Okay, and the first copy of the signal. Okay, so omega s is 2 pi by Ts, that is equal to 3000 pi. So, my sampling frequency is here. Okay, so the first copy of the signal will be original spectrum shifted by the sampling frequency k times omega s, where k is equal to 1. So, the shifted spectrum will be plus minus 4000 of the sampling frequency. So 1, 2, 3, 4, no, I marked it on the wrong one. It should be on 3000. So the first copy of the signal will be at 7000 and it will be at minus 1000. That is corresponds to k equal to 1. The blue corresponds to k equal to 0. I presume that is the same notation that we have used in the last case also. Now quickly draw the case for k equal to minus 1. K equal to minus 1 will place a signal at plus 1000 pi. It will also place a signal at minus 7000 pi. Okay, so this is minus 7 and plus 1. This is minus 1, this is minus 4. So again we get a replication of spectrum, except that now the images seem to have been interlaced. Whether it is a problem or not, we do not know yet. Let's figure out the heights of these So basically each of these will be at a height of pi over Ts. Okay. Now the reconstruction filter says, so let me write down here, reconstruction filter says it goes from minus omega s by 2 to omega s by 2. Okay, so that basically means that the filter will go from minus 1.5 to plus 1.5 when you multiply it on a by 1000 pi on the scale. So the reconstruction or the filter that we are going to be working with, this is one. So the reconstruction filter goes like this with a height of Ts and reconstructs this. So effectively what we have obtained through the reconstruction process is, what is that frequency? It looks like cosine 1000 pi t. I sent in a signal cosine 4000 pi t, sampled it at 1500 hertz, obviously aliasing was present. I applied the correct reconstruction filter for my sampling rate and obtained, and it looks like, okay. Now please make sure that we are comfortable with this. Cosine 2 pi by 3n, that is the discrete time representation. We know that omega naught prime is equal to omega naught by Ts. Okay. So so cosine omega naught dash t, that is the reconstructed signal, will be equal to cosine the discrete time frequency, which is 2 pi by 3 times divided by Ts, that will be multiplied by 1500 times t. If you look at it, it actually is cosine 1000 pi t. Okay. So basically you need not have drawn the spectrum, you could have just gone with the relationship between the sample signal and the sampling frequency, and you would have gotten the same expression. Okay. Now there is one more example that is related to this. By the way, this is an example that is present in Oppenheim and Schaefer chapter 4. What we have discussed is example 1. A closely related example 2 is also present. Again, it is just a minor variation of that. So what we have already looked at this. I would like you to suggest that you can take a look at this other case. Okay. Now let me just frame the reconstruction problem that, or the task of reconstruction. So the task of reconstruction, which we will build on the next lecture. So the reconstruction process, we have completely understood the sampling, the effects of undersampling, effect of aliasing, how the images form, and how we will reconstruct using the reconstruction filter. Now what we have is a continuous time signal that has been sampled at omega s. Sampled at omega s. Now, whether it was band limited or not, let us say that you have sampled a signal and you've got a sampled signal at omega s. Now, when I reconstruct, or when you reconstruct this signal, there is no notion of frequencies above omega s by 2, because as far as we, in our world, if you tell me it's a discrete time signal sampled at omega s, then to me there is no frequency above that, because whatever frequency was, the information was there, already got aliased down, and therefore, so the reconstructed signal, this is an important statement, the reconstructed signal will be band limited. You cannot reconstruct a non-band limited signal, because by virtue of the sampling process, you have said that, okay, sampling can only preserve the information content up to a certain, half the Nyquist frequency. So it is a band limited signal from minus omega s by 2 to omega s by 2. First and foremost, that is the key. And of course, the way we draw this filter, we have drawn it a few times already, minus omega s by 2 to omega s by 2. Now, can you relate omega s by 2 to the sampling frequency? Yes, we can. Omega s is equal to 2 pi by Ts. So, if you want me to write it down, this will be minus pi over Ts to pi over Ts. So, I have a simple task for you. If this is my reconstruction filter HR of t with a height of Ts going from minus pi by Ts to pi over Ts. So, the reconstruction filter HR of t inverse Fourier transform 1 by 2 pi minus pi over Ts to pi over Ts. It is a flat signal with amplitude of Ts, e power j omega t d omega. Okay, that is my reconstruction filter. Please do verify that what you get is HR of t is of the form of a sinc function sin pi t by Ts by pi t by Ts. Okay. Now, this is a very important filter, very interesting filter with a unique structure. And why is this structure important? How does this structure play a role in the reconstruction process? It is a infinite impulse response filter. It is a non-causal filter, but this is what we get as the ideal reconstruction filter. So, how do you make this a realizable practical filter? Those are all very important questions. We will address them in the very next class.